Good morning, students. I guess we're in the classic Houston area wintertime, cool in the morning, warm in the afternoon, and I'm grateful for that. It's great to run in the morning when it's cool, and then the afternoon you can just walk out with a long sleeve shirt and you're ready to go. So I guess this part of Texas is the Florida that we all like to live in. So I'm grateful for the nice weather and the lack of all this rain. So that is a blessing, hopefully for now. But by saying this, I'm like I always say, I jinx things, and then we'll be back into some bad weather. But I'll keep my fingers crossed. What we want to do today is just kind of move through uh, on into the continued convergence theorems about infinite series, so we can basically wrap up this chapter and then go on into chapter 10 and completely switch gears on parametric equations and polar coordinates. I think you're really going to like that chapter because it uses some trigonometry and also some calculus from your Calculus 1 days. I think it'll be a nice refreshing change, but we're not there yet. So the first thing we want to do today is to talk about two tests, the root test, which will be the second test, and the ratio test, the first test. They're related. We'll talk about some of the theoretical ideas in the ratio test, and in the root test, I'll let you use the class notes to look at some further ideas there. The nice thing about the ratio test, and let me go ahead and share this with you, is that it's a test for absolute convergence. And most students really enjoy this test. So first, what I want to do is just share the statement of the theorem, and then I want to do an example, and then I want to talk about why it actually works. This, again, when we do tests like the geometric series and all, we find that particular series is indispensable. And also the telescoping series are indispensable. You found that out in Calculus 1. And so it's nice when we actually have a test that reminds us of those, that's easy to employ. And basically all of the tests so far have been fairly straightforward, but this is one that I think you will like. And in your textbook, this is theorem 9.17, and the statement is very, very simple here. I wrote this out so you can easily see this. Now, the hypotheses for this particular test are fairly slim. It's not like the integral test where we've got so many hypotheses, it's hard to keep up with them. Basically here, we just want a series with non-zero terms because we're going to need to take ratios as evidenced by the actual name of the test, the ratio test. So we just start out with a series of non-zero terms. Now, what's simple about the test is we just look at the limit of this ratio. It's like we're thinking about a geometric series where we have a common ratio when we compare successive terms in the sequence, and that ratio is always the common ratio R. Here, just a little bit more complicated, but not much. We look at the ratio of two successive terms, a sub n plus 1 divided by a sub n. But again, this is a test for absolute convergence, so we look at the absolute value. So again, maybe we will be nullifying some change in sign or whatever. Sometimes we don't, but that's okay. We know that the test for absolute convergence is something that we actually studied with with the alternating series test. And so this is one of those tests where you get a twofer. Not only do you get convergence, but you get a more powerful result, which is absolute convergence. And of course, if the series is always just positive terms, it seems like a moot point, but still, this is a powerful test. Now, if we show that this particular limit of this ratio is less than 1, then we have absolute convergence. So just like the limit comparison test, we want to actually compute a limit. Remember, with the limit comparison test, we just needed a limit that was positive. Here, we need a limit that's positive, but it must be less than 1. So a little bit of a change, but some similarity. Now, and this shouldn't be any surprise to you, if we take the limit of this absolute value ratio and the limit is actually bigger than 1, then the series diverges. And that's basically the divergence test. I'll say more about that. That's the easy case. Unfortunately, when you get this, you go back and check to make sure you didn't leave out a factor somewhere that could have made this less than 1. Because at this point, you're like, okay, well, you know, it diverges, I'm done. But again, just remember, though these tests are very straightforward, just like the integral test or the geometric series test or the comparison test, we have to make sure that all of the arithmetic is aligned properly so that we get a good result. Now, the next one is going to surprise you, and it was always an interesting case for Professor Ron when I was a kid. The limit here, when we get identically 1, and it will happen, then we have no conclusion. And the proof of this part is very simple. Again, we just compare 2 series of your choosing or my choosing. It's a very simple proof. But the thing is that you look at this and say, well, you know, we've got all these nice results here, but when we get the case where the limit is identically 1, then we can't give a conclusion. And so we have to look at something else. You can't say, well, it almost converges or it almost diverges. You know, in real analysis with the study of infinitesimals, we can't do that. We approach from the left or from the right, and there are an uncountably infinite number of real numbers in any interval aside from the singleton interval in the real numbers. So that's why we study the calculus with the real numbers, because of the continuum status that we enjoy. So interesting for number 3. So again, doesn't happen a lot, but it will occur. Now what I want to do before we talk about the actual proof of this, and it's very straightforward, I think you'll see why Professor Ron likes the geometric series, but I just want to do a simple example of this as an application before we actually do a theoretical justification, because I think you should see it. The ones that we do, ladies and gentlemen, actually employ techniques that you already understand, and it helps your understanding. I was looking at your test, and I'm very pleased that you all are understanding the process. And I look at your work that you submitted, and it shows that you take good notes and that you listen to what I say. So I appreciate that. Again, I always strive to have notes or your work that is detailed enough so that I can follow your work. But as a dry run for this test, I was pleased. Now, let's look at a particular example. Now, just because we're using the ratio test, you might be thinking, why would we want to use the ratio test over some other test that we've already dealt with? Well, let's just look at this particular series here. We have the series n equal 1 to infinity of the generating sequence, in this case, excuse me, too many wires, let me move this paper over. We have n to the 4th divided by 2 to the n. So we've got a positive term series, but probably an inequality wouldn't be the simplest way to go. Maybe the limit comparison test, no, because we don't really have a good series to compare this to. But what we do notice here is that we've got lots of powers. We have a power function and we have an exponential function that deal well with the ratio test. And then of course, we certainly don't want to integrate that. So again, lots of times the ratio test will present itself very quickly because the other tests that we have just don't seem to fit very well. And we need to make a conclusion. So what we're going to do is, what I'll say is test for convergence. And with this example, we will use ratio test. Now, of course, this doesn't have a change in sign, but we still utilize the same technique. We always write this down. So we look at the limit as n approaches infinity. And if you like here, just go ahead and write the generating sequence down. N to the fourth divided by 2 to the n. So this is where we just get to use laws of exponents, which you know since Algebra 1. So even though maybe they weren't proven or justified, you learned how to use them. So we have the ratio of a sub n plus 1 divided by a sub n. Now, in order to affect a clean algebraic strategy, what I like to do usually when we've got the generating sequence being a ratio already, we can flip it. This part we see, we have a visual of a sub n, so we can reciprocate and multiply just to cut down on having a complex fraction. So now first, we replace n with n plus 1. So that's the easy part. So n becomes n plus 1, like we're doing an index change in an infinite series. And then here we replace n with n plus 1. So the execution is pretty simple. Now we want to divide by a sub n, so just reciprocate and multiply. So we'll have 2 to the n divided by n to the fourth. Okay, now of course, these are all positive terms. Let me adjust the focus. There we go, that looks better. Your eyes are much better than mine, but if it looks blurry to me, you're probably like, oh, Professor Ron, I can see it, but I want to make sure it's clear. Now, what we're going to do is align these in a way that makes them easy to basically manipulate. And then plus, of course, this is just positive, so we can remove the absolute values. So let's just go ahead and put everything together. We have 2 to the n, equal opportunity grouping, as they say. So this is just 2 to the n times 2 using the laws of exponents. And then, of course, we have n plus 1 over 4 divided by n to the fourth. So now, of course, we'll have the limit as n approaches infinity. Of course, the 2 to the n's absorb, and we're left with a 1/2. And then, of course, we can write the umbrella of fourth power, n plus 1 divided by n to the fourth. Now, of course, we're just back to calculus 1, where you didn't know much, but you hopefully worked hard. We can factor the 1/2 and move the limiting process inside by continuity. We just have a simple power function, which is continuous for all n, especially just the positive integers. So we get 1/2, and then we have the limit as n approaches infinity of n plus 1 over n raised to the fourth power. And now, of course, the 1/2 is fixed. And then, of course, here, the ratio of leading coefficients just gives us a 1. So we get 1 to the fourth. So this is 1/2 times 1, which is 1/2. Now, of course, again, some of you are very meticulous with your work. Others don't put in enough steps. And if you kind of slim in that area, you need to improve on that. Again, this was a dry run. So if I make a comment, it's not going to impact your grade. But if I make a comment that, you need to include more detail, maybe some medium between a lot of steps and no steps, just hit somewhere in between. So now we see that the limit of the ratio here that we have in absolute value is clearly less than 1. So you can do this if you like, just to kind of make the point that you've utilized the theorem. Then we'd say the series. At this point, you don't have to always write the series again. We say the series converges absolutely. By ratio test. And since we're going to have a root test, we can't really do RRT because you wouldn't know. I mean, clearly by context, the person would know, but that's okay. Just, you know, so what we see here with the ratio test is it reminds us of our Calculus 1 days. The limit is fairly straightforward, but you're thinking, you know, what's going on here? So I want to say a little bit about this. And so I will say this, as you do your work for these sections, you're going to find that the execution goes a lot quicker and that you're going to find the ratio test to be your friend. Now we're going to have adjustments on the ratio test when we talk about power series in general. But I never tell my students, well, you've got to do it this way or you've got to do it that way. My choice is that you have a strategy that's effective for how you understand the material. And that's what's most important. So let's just look at what we might do if we were thinking about some form of a justification of this particular method. Now, what I want to do is just make a couple of comments here. We won't do this for the root test. It'll be a similar proof that you can look at the notes and go through that because the techniques are very similar. So we might say, why is this a good method? So what we want to do is first, if we look at this, we know, let's just go back to the statement here. We know this limit is less than 1. It's obviously, in this particular case, these are positive terms. So we're thinking, okay, as we start moving along, or for instance, we have non-zero terms, we're thinking we've got a limit that is less than 1, but greater than 0. Now, of course, if you look at this and you think about this particular technique, you're thinking, oh, well, we're going to be less than 1. And so that's going to open the door to the geometric series, thinking of a common ratio. So now what we're going to do is this. And I'll just say, there exists, it'd be a little bit more formal in my writing, there exists an R between 0 and 1, such that the actual limit, in this case, as n goes to infinity, of a sub n plus 1 divided by a sub n equals R. Okay, so that's a fixed real number right there. This is, because it's a limit, it's unique, so this is fixed. And now we're going to fix another number. So we're going to fix an uppercase R. In this case, I'll just say this is in the real numbers, such that what we want to do is sandwich uppercase R between lowercase r and 1. Which we can do by the continuum of the real numbers. If we have a number less than 1, they're an uncountable infinite number of numbers between said number and 1, which again is why we love the real numbers for the calculus. And here's what we're going to do. This is going to give us an epsilon, because we need an epsilon to show that we actually can provide some kind of reasoning why this particular infinite series will converge. And we're going to set epsilon equal to the difference between uppercase r and lowercase r, which is clearly positive. So this is convenient for our reasoning. Everyone always says, well, why do we do this? And my comment is, it works. Mathematics doesn't mean that the idea is going to just drop into your lap. It just means that if you learn a technique, you grab onto it. If you're working with limits and you need a positive tolerance, epsilon, then pick one that's going to be involved with what you're working with. It will move the logic forward. Otherwise, if it's too arbitrary, you don't get anywhere. So now what we want to do is apply the definition of limit. This limit exists. So by definition, there exists, and we're going to have a greater than or equal to because we can be flexible with that. Let's just pick an n for which we know this works. There exists some natural number n such that when n is at least big N. So we've got this tolerance. We could have greater than or equal to, go out far enough so we can start with a natural number that works. This implies that the actual generating sequence here, that is the absolute value of a sub n plus 1 divided by a sub n, is within epsilon of the limit. And our epsilon is big R minus little r. And just like before in the limit comparison test, we're going to look at the part of this conjunction that helps us move forward. So what does this say? Well, now this is a positive tolerance absolute value. This is a conjunction. So we take the additive inverse of this. We don't care about this side, but when you flip it around, you have the additive inverse. And you have a sub n plus 1 divided by a sub n in absolute value minus r is less than big R minus little r. Okay, so this is true, but not very useful. I mean, you know, it doesn't mean we don't care about it, but it's not going to help us with our argument. So what we're going to do is focus on this part, like we did with the limit comparison test. So if and only if, notice the r's absorb, and we have a sub n plus 1 divided by a sub n in absolute value is less than r. Okay, we'll keep going because we want to develop a recursion. So then the quotient of absolute value of your quotient is the quotient of absolute value. So we're going to cross multiply. So we have an r times the absolute value of a sub n when n is greater than or equal to big N, so to speak, uppercase N. So this is the key here. Now, what's interesting about this particular problem here is that once we have this, we know eventually this is always going to be true. So we've got n, well, actually, if you consider this n minus 1 terms, a sub 1, a sub 2, and absolute value up to a sub n minus 1 in this particular case. Well, and actually up to a sub n, because this is going to start with n plus 1, that are just finite. Finite sum is convergent. I mean, that's the simplest thing in the world. I mean, if you add up finite real numbers, that's a real number. I don't care if you add up a billion of them. That's a real number. That's a finite sum. And so we just have to figure out that what's left, the tail of the series, as n tends to infinity, that we can control that. And we can because we're going to have a geometric series to compare it to. So now just to see how this works, this, again, I want you to understand. I'm going to find some way to test you on some of this. So when I say understand it, I mean that. And it doesn't mean that I'm going to put it on the test. It means that there is a possibility that it might occur. So I do want you to understand this if I bother to go over it. Because again, I'm just using techniques that are straightforward. Calculus is not mysterious if you don't shy away from understanding the theory. So now we're thinking, okay, well, what does this give us? Well, a sub n plus 1 in absolute value is less than r times a sub n. Okay, well, okay, so Professor Ron, you just replaced n with big N. Okay, well, what about the next one? A sub n, I'm not going to like say, oh, it's obvious, because it's not. This is less than r times the absolute value of a sub n plus 1. But a sub n plus 1 is less than r times the absolute value of a sub n. So we'll replace and say less than r squared times the absolute value of a sub n. So now you're thinking, oh, I see what you're doing. You're generating powers of r, and r is between 0 and 1, common ratio bit. And then now you see the deal. We're developing a recursion. So now by comparing this, the next one, a sub n plus 2, or excuse me, n sub 3, comparing it to this, we'll get this. Here we have the square, here we have the singleton or the 1. Now we can just jump. We've developed a pattern enough that we say, well, this is going to be less than r cubed times the absolute value of a sub n, etc. So here's where I write a recursion. And I'm going to use an I. So a sub n plus I will be less than, in this case, I'll just go ahead and write the absolute value of a sub n first, since I did it that way in my theory. I'll have r to the I, where I is greater than or equal to 1. So when I is 1, we get this one. When I is 2, we get this inequality, 3, etc. So this gives us a nice recursion. I told you this was very straightforward. Now, most students say, well, Professor Ron, I would have never thought about this. Well, that's where you develop techniques. Ladies and gentlemen, the first time as an undergraduate at Carolina, I had a visiting professor from MIT at the University of North Carolina at Chapel Hill. The guy was brilliant, and we were like, what is that? What is he talking about? What is he talking about? You know, but we took notes and we studied and we went to his office hours and we figured it out. But the first time you see this, it is a little bit quirky. But back then, it was like, you know, you got a little bit and you were expected to do a lot. Now we give you much more than we got at the time, because that's just how education has evolved. But the thing is that as you go through this several times, you'll be like, you know, I get this. This does make sense. Now, what we want to do is say, okay, how does this compare to the original series if we're thinking about absolute value? So let's write it down. So now we'll look at the absolute value, a sub n equals 1 to infinity. Now, this takes care of a sub n plus 1, I, where I is 1, 2, 3, 4. So we're going to just write in the first n terms. I'm just going to write them, you know, I'm going to make this very user-friendly. Keep it really simple. Every time I write a sum, you all are like, oh, don't write a sum, that's confusing. Well, I'm going to write some sums, but I'm going to keep it simple right now. So this is going to be, I could have just written a sum here, but again, I think this will make it a little bit easier to see. But I want you to get used to that summation notation. And now we're thinking, okay, well, that's the first n terms, and now I'm going to tack on these. And I'm going to write this as a sum. So here we will have like, I guess I can use an n, and it doesn't really matter, n equal, let me do this way. Let me do n plus 1. So I'll start with n plus 1 here. That'll work. So you're thinking, well, that's not very smart, Professor Ron. That we know this. You didn't do much. So here are the first n terms, and then this just starts with n plus 1. But we have an upper bound on these generating sequences. So now we can use this. So this will be less than, and now I'm just going to write this as a finite sum. So this will be, say, n equal 1 to uppercase n. Right there, these are equal. And then I'm doing the upper bound here. So this will be less than, well, we've got the less than, so plus. So put in the upper bound for this right here. So let me write this in. And this will start, I'll use another n, it doesn't matter. Well, this will be n. So n equals 1, in this case, to infinity. So now what I've done is replaced all of these with their upper bounds. That is the number, absolute value base of n times r to the n, starting with 1, 2, 3, 4, etc., getting all of these guys here. But now this is just finite, so I'll just write it again. And now, of course, this can be factored. It's just a constant. And then I've got a geometric series, which you all did well on the test. I was very impressed. Now, of course, here we have n equal 1. So this is one of those ones where A is R and R is R. And I'm sorry, I'm abusing notation here. These are not, we got different R's going on here, but that's the notation I use with the infinite series. So we have, in this case, this equals this number here, that finite sum, which is clearly convergent, plus, and now the sum of this will just be A sub n. So that would be, in this case, A divided by 1 minus R. So this would be R times 1 minus R. Now, when we look at this, we say, okay, this is a real number. So this is a real number, element of R, or less than infinity. So basically what we're saying is when we look at this, we're comparing it to this series here. This series is being compared to this series, but we just showed that this series converges. Okay, so again, let me say that one more time. This series is compared to this series. This series converges. So by the direct comparison test, this series must converge. So that wasn't so bad. So let's write it down. I told you this was very straightforward. That's why I wanted to go through it. So now, by direct comparison test, this series converges. And of course, this implies that the given series converges absolutely. So that's why the ratio test works. And that's just, when you think about it, ladies and gentlemen, that's basic arithmetic. There is nothing going on here except basic arithmetic. And I don't need to number my notes. That's bad. The notes I make in class, I don't number. I put them in a pile to use later if students have questions about them, but I can't number them because my lecture notes are numbered, then I get confused. So I've got to maintain proper technique. Another issue of being a math professor. Now, for the other parts, and they're simple, and we'll do a couple more examples, then we'll talk about the root test. For instance, suppose that the limit as n approaches infinity of this particular ratio is greater than 1. Okay, so we're going to do the same thing. So by definition, there exists some natural number n such that in this particular case, n greater than or equal to n implies, and this is actually very interesting in the sense that since this is greater than 1, there comes a time where we just do the cross multiplication, so to speak. That is, a sub n plus 1, just like we did before, is actually greater than a sub n. So we can get out far enough so that we're assured of this limit. And so then we can just look at this and say, okay, well, that means that this quotient is actually bigger than 1 eventually. And that would mean that the term following this term that is in absolute value is going to be bigger. So now what we see here is we have a monotonic sequence. That is, this is a non-decreasing sequence. Hence, this sequence, if we look at it in the absolute value, is non-decreasing. So again, it may jump around in sign or whatever, but now it's non-decreasing. So this implies that the limit as n approaches infinity of a sub n is not 0, which also implies that the limit, if we just took the absolute values away, maybe we get 2 divergent sequences of a sub n is non-zero. So if in absolute value, these particular terms in here are getting bigger, then there's no hope for this to have limit 0. If this doesn't have limit 0, then there's no way that this could. And again, if this is already a positive term sequence, we're done. And if it's alternating in sign or jumping around or whatever, it's still, we would have a subsequence that would not go to 0. And if you've got subsequences not going to 0, the whole sequence could never go to 0. So that's basically common sense. So again, we see divergence by divergence test. So this is like when you're trying to use the alternating series and you show that the limit is non-zero, you know, or not equal to 0, then you're thinking, oh, I think I just used the divergence test here, not the alternating series test. So this comes in very handy. We know that if you have a convergent series, the generating sequence must have limit 0. So in contrapositive, if we show that this limit is actually non-zero, we're done. We know the series converges. So remember, this is the contrapositive form. This is a very important series test, the test for divergence, that saves you from having to do any great amount of work. And when it's there, you take advantage of it. So this was easy. This didn't require, you know, the geometric series and all that arithmetic. This just required looking at the fact that eventually this will be true if this is true. And so we think, okay, well, that's a non-decreasing sequence, and then we're kind of cooked at this point. So this is an easy proof, but it's a little bit, again, when you think about what we're doing, we always step back and say, well, is this exactly what we're trying to say? Absolutely. But like I say, the first time you see it, you have to step back and say, okay, I see what's going on here. You know, when we think about sequences, it doesn't matter how many convergent subsequences you have. If they converge to different limits, you're done. The sequence has no limit. So that's what we're using here. So for number 3, this is the easiest proof we've done all semester. So here was what we want to do, and I'll let you verify this. Consider, we'll look at it, consider these series. And I think what I picked here was one that you know very well, the harmonic series, and a convergent P series where n is equal to, or excuse me, P is equal to 2. Now, why am I doing this? Well, let's just look at this. We'll call this I, and we'll call this double I here. So for instance here, if we look at the limit, I won't have you do it, I'll just do it. Well, that's ridiculous. So we'll just say a sub n plus 1 divided by a sub n. So again, this would be 1 over n plus 1, replace n with n plus 1, then reciprocate the 1 over n. That'll give us n over 1. So this will just be the limit as n approaches infinity. Again, remove the absolute values. These are positive terms. Ratio of leading coefficients. That's just 1. Okay, well, let's look at 2. Let's look at the limit as n approaches infinity of a sub n plus 1 divided by a sub n. So we have the limit as n approaches infinity. Now, of course, we'll replace n with n plus 1. So we get 1 over n plus 1 squared times, and then we divide by a sub n. So that would be the reciprocal, n squared over 1. Again, we can remove the absolute values. So this will be n squared over n plus 1 squared. And now we can just use continuity and move the limit inside of the umbrella of the square. So this part is just n over n plus 1 squared, and then move the limit process inside like we did before. So just remember, this part equals n over n plus 1 quantity squared. Move the limiting process inside. And of course, that limit, again, just like this one, is 1. So we get 1 squared, which is 1. So what we're seeing here is that it doesn't provide a clear conclusion, because we know, we know this is our famous divergent series, and this is convergent. So the limit of 1 doesn't give us a conclusion that's reliable, because as we test it with just 2 series that we certainly know convergence or lack of, we get the same result. So what we're seeing here is that this test is not half bad. You're always frustrated when you get 1. You want to finish the problem. You want to move forward and say, I want to be done with this example, and got to try something else. So the idea here is that, again, when you think about tests that you've already done, we're amassing different convergence tests. And so you can now say, okay, well, I could use this test, but it's kind of difficult. And if I tried to integrate that, that'd be more work than I want to do. Can I use the ratio test? I don't want to use the limit comparison test. That limit would be a little bit difficult. That's a special limit I haven't seen, so let me try this. You know, you do have L'Hopital's rule, but again, what you're going to find is that the ratio test is a very, very convenient test, and it's the twofer, because once you get the convergence, that automatically gives you absolute convergence. So it's as tests go, it's a good test. And what does good test mean? Well, it just means it's a test that you can utilize in a very straightforward manner. So let's look at an example. Let's see here. Let's look at a factorial, and then we're going to look at a alternating one in terms of products. And then I just want to give you the example of the root test. So here's a good example. Or I'll state the root test, and then we'll do an example with that. It's real easy too. So notice in this particular case, this is again a positive term series. We have n factorial divided by n to the n. And we want to test for convergence. Test for convergence. So now again, the powers, n factorial, not something we want to do the previous with because of that n to the n. So we're thinking that we might be better off utilizing the ratio test. So we'll just say use ratio test. It doesn't mean you can't try something else, But again, I think what we're seeing here is that this might be simpler since this end to the end is not giving us a nice comparison like with the convergent or divergent P series. So might be best with the ratio test. So now we have the limit as n approaches infinity of a sub n plus 1 divided by a sub n. So we have the limit as n approaches infinity. So now, of course, here's our a sub n. We just replace n with n plus 1. So we have n plus 1. That's the easy part. I mean, this is really simple. N replaced with n plus 1. And then we get n plus 1 raised to the n plus 1. So replace n with n plus 1. And then we reciprocate, divide by a sub n, so just flip it. So this is n to the n. And then we have n factorial. Now, of course, these are all positive, so you can remove the absolute values. No need to drag them along. So we have the limit as n approaches infinity. Now what we want to do is pair these up in a way so we can use some algebra. First, we're going to notice that we have what? N factorial, n plus 1 factorial would just be n plus 1 times n factorial using definition of factorial. And then, of course, n factorial is just n factorial. And here, and this is where you think about what you have here and what's going to be simplest. Now, notice here we want to use the laws of exponents to pair this off so we can kind of put these under the same umbrella. So let's think of this as n to the n, and then we'll say n plus 1 to the n, and then put the extra power of n plus 1 or factor of n plus 1 over here. So n plus 1 to the n plus 1 is n plus 1 to the n times n plus 1. So that way we actually get more bang for the buck. Again, the laws of exponents will be heavily utilized in the ratio test. So again, very simple, but you're going to have to get used to doing this. Kind of like doing L'Hopital's rule and limits in Cal 1, but we haven't been doing a whole lot of this. We've been doing a lot of manipulation, but now we're getting back to your roots where you didn't know as much, but you were good at working with powers. So now what we can see is that the n plus 1 here, these absorb. And then notice the n factorials absorb. So we're like, wow, everything goes away. So we have the limit as n approaches infinity. And so now we have n to the n. So this is the same umbrella type thing we had before. So all of the other riffraff is gone. And so we can write this as under the umbrella of n, so to speak. So this is the limit as n approaches infinity of n over n plus 1 to the n. Now at this part, and this is where I made a couple of adjustments. And what I want to do is to look at this in terms of a limit we've already done. This is looking a whole lot like e, the exponent or the natural base, but we don't have exactly that. So we're going to do some little change of exponents, so to speak. So notice, let's flip this over so we know we have an e. So this will be the limit as n approaches infinity. In this case, of n plus 1 over n. And now, if you like, let's move the n here, and then the negative 1 outside. So notice, if we flip this, we take on a negative n. But now we can use the laws of exponents and flip things around. We know what this guy is, that's e. So, and the negative 1 is out here, which is, again, part of the composition process. So now notice, we can move the limiting process inside by continuity. We're not going to be hitting any zeros here, so this reciprocal function will be fine. So we have the limit as n approaches infinity. In this case, this is just n plus 1 divided by n. So let me write it in the way you're used to seeing it. So now you think you're back in pre-cal or college algebra when you were doing interest problems. So you might look at this and say, oh, well, that's just e to the minus 1. Well, of course it is if you've seen it a lot, but now this is why you do get that. And later on, you might say, well, that's something I've seen before. And then, you know, you could get e to the minus k if you have certain coefficients here. So that, again, the idea is let's make this look like something we understand. Now, of course, this by definition is e. So we get e to the minus 1, or just 1 over e. Well, e is clearly bigger than 1, so this number is actually less than 1. So in this case, we didn't have sign alternation, or we didn't have some terms that were positive and some terms that were negative, so the absolute values went away. But what we're seeing is that we do have convergence. And this, my friends, actually is less tedious than doing an integral or working with an inequality. You tend to be better at limits. And so now the series converges absolutely. I mean, you know, absolute value, that's still the same thing, absolutely, by ratio test. Rather a remarkable result, just utilizing concepts. And again, you know, you can prove that this is e using L'Hopital's rule, taking logarithms like we've done before, but we kind of take this as the definition of e and don't have to worry about it. We're done. I mean, we don't usually like to apply L'Hopital's rule to this because this was our actual definition back in college algebra and pre-cal, but you can do it if you like. You'll get the same response. So again, a very nice result using the ratio test. Now let's look at another example, and then I'll give you the statement of the root test. So this one actually does have some sign change, so maybe you'll feel a little bit better. So here we want to test for convergence, and this is written in terms of products. We'll have some nice formulas. WebAssign gives nice formulas for some products that we'll find useful when we talk about the convergence of the binomial series. So this one actually is going to alternate in sign. Maybe not like we're normally used to. We usually, with the alternating series test, we have n plus 1, but that doesn't matter. So now upstairs, we have 5 times 10 times 15. So this is written as a product and no formula for the product, so that's good. Product formulas are tricky. And then we have 5 times 11 times 17, ascending to 6n minus 1. Now this is where you think, okay, well, I want to test for convergence. And if there was ever a useful test here, it would be the ratio test. That nothing else we've done so far would attack this in any kind of way that would give us what we would need. So when we test for convergence, we think, okay, this is a good example for the ratio test. So in this case, use ratio test because nothing else is going to work, at least at this point. So now let's do this. Notice here, and this isn't required, but look, there's a 5, and we start with 1, 2, 3 of the n. There's a 5, and they're n factors of 5 here. You can factor that if you want. You don't have to, but it's kind of in the way. I don't know. You can leave them alone if you like, but that's kind of bugging me. So this is really just 5 to the n. So we have 1 times 2 times 3 to n. Not that that's any kind of earth-shattering observation. I don't think it's going to make any difference. When I saw this problem, I said, well, we just need to factor this, but you don't have to. it's weird when you look at a problem a different way, you think, well, you know, let's just change it up a little. Let me refocus here. So now when we think about this, we look at this and we say the ratio test is the best avenue to take. So we'll have the limit as n approaches infinity of a sub n plus 1 divided by a sub n. So we have limit as n approaches infinity. So now we just do the replacement of n with n plus 1. So we have negative 1 to the n plus 1, 5 to the n plus 1, and then 1 times 2 times 3. And then, of course, the n becomes n plus 1, so we have an n times n plus 1. You don't have to put the factor right before, but it's clearly there. And here we have what? 5 times 11 times 17. And then we have the n plus 1. So this is going to be 6n minus 1. And then we get 6 times n plus 1 minus 1. So that's the new term, so to speak. And now, of course, we just reciprocate the a sub n. So usually we call that a u sub n when it has the alternating sign, but that's the statement of the theorem. So flip everything over and we'll just use this one. So this will be negative 1 to the n, 5 to the n, 1 times 2 times 3 to n. And now, of course, this comes upstairs, 5 times 11 times 17. So you can see here that we're like court reporters at this point. We just keep writing the same thing down over and over, but at least we know that this is going to get us where we want to go. So now when you think about this, this part here, I'm just going to write to the side in absolute value, negative 1 n plus 1 over negative 1 to the n. That's just the negative 1 to the n's absorbed. So that's just the absolute value of negative 1, which is 1. The rest of the stuff is positive. So we took care of that. You don't even have to write this step. I mean, it's clear, but for now, just see we've retired all of the negatives, so to speak. And what's left here? Well, you know, we don't even have to do equal opportunity so much. Notice that we don't have to go ahead and write everything down again because we can clearly see that these factors will absorb. Now, well, but of course I'm going to write it anyway. So let me write it down anyway so it's clear to everybody. Every time I say, well, let me do this, I'll just go ahead and write it. And so just do equal opportunity like I did here. And now if we look at this last one, this is going to be a 6 to the n, and here we've got a 6 minus a 1. So this is 6n plus a 5. I mean, that's clear because these all differ by 6, so that's not surprising. Here, 5 minus a negative 1 is 6. And then let's put these guys together. So we have 5n plus 1 over 5 to the n. So we've checked these off. And then we have, that's it. I mean, and then of course, this part is left. So we have 1 times 2 times 3, ascending to n plus 1. And then we have 1 times 2 times 3 to n. So now, like I said before, this is 1, the absolute value of negative 1. We're done with that. All of this absorbs except for this. So what are we left with? We have a 6n plus 5. Here, we're left with what? 5 to the n's absorb, and we're left with a 5. And then, of course, here, the 1 up to n's absorb, but we're left with an n plus 1. So you can see the ratio test is like tremendous here. So now, if you like, we're pretty much done. We could factor, but we've just got the ratio of leading coefficients. This is degree 1, this is degree 1. So this is clearly 5/6. Now, I will say this, when you're doing problems like this, of course, you might be tempted to factor the 5, and then you've got 1/6 times 5. It doesn't matter. At this point, I think I would just do something like this. I just say this is 5n plus 5 divided by 6n plus 5. Maybe write it that way, and then ratio of leading coefficients. Maybe that would be an easier way to get the limit without error. And then, of course, this is clearly less than 1. So now we see here, maybe this is the first example where, well, it's the third example, but clearly here, you wouldn't have thought about any other test. That would have never come to mind. And then you're thinking, well, this is an alternating series. And it's like, well, you know, I could try to show that it's non-increasing and show that the limit is equal to 0, but that would be rather daunting the way it's written. This ratio test clears up the clutter, so to speak, and leaves behind something that's easily recognizable. So here we have the series, but again, if you only have one option open to you, you make it work. We just chose the easier option. Series converges absolutely by ratio test. So not only does this alternating series converge, you can clear away the alternation of sign, and that series converges. So this is clearly a powerful test where you get a twofer, so to speak. So that's an excellent example. Again, I'm sure you will master it like all of you do. Now, one thing I want to do here, I want to actually talk about the root test. Now, what's good here, I've got a nice little example with a L'Hopital bit that we've done before, but let me find the statement here of the actual root test. I think I stuck it over here somewhere. Here we go. Now, when I put this down, you're going to look at this and say, okay, this is exactly like the one we've just done. But we don't really care. We don't really compare. I mean, we could have some 0 terms, but usually that's not going to happen. And you're thinking, where would this test be good? I mean, can't we just use the ratio test? Well, if we have powers of n that can be eradicated by taking an nth root, well, that's pretty good. So the ratio test will have a more far-reaching application than the root test. But the root test is so similar to the ratio test, and I encourage you to look at the notes, that it's like, okay, fine, Professor Ron, if I need it, I'll use it. The nice thing about it is that it will present itself because it will put forth limits that you know how to do. Maybe you use L'Hopital, maybe, you know, there's some simple, like we do ratio of leading coefficients. The idea is that the root test, though the application is smaller, the smaller scope, it's very obvious when it would work. So here we just need a series, preferably something that doesn't have just a bunch of zeros in it, clearly, but we don't need the fact, if some of the terms are 0, we don't care. That's usually not going to happen because we're not taking ratios. And we're doing absolute value. So this is kind of like the convergence test with no hypothesis. I mean, it's like, how does this work? Okay, well, so when you look at the actual justification in the notes, you'll see how simple it is. It's just like the root test proof. So how does it work? You see this? It looks exactly like the ratio test. So we'll start out with the limit of a sub n in absolute value to the nth root. That is the 1 over n power. Remember, when we do a sub n to the 1 over n, we're lazy because we love this fractional equivalence, like square root and 1/2. Even though we like to write square roots, this is the nth root. So if we're doing it in a very formal notation, sometimes some of you all use this in WebAssign, you have the nth root in this case. So you're thinking, if this a sub n has some powers of n in it, this 1 over n is just going to eradicate them. It's like squaring a square root. And so that would be somewhere where the root test would be more appealing. Now, with the notation set aside, you can see that in this case, the cases are exactly the same. If we take the limit as n tends to infinity of the absolute value of a sub n to the 1 over n power, and it's less than 1, then we get absolute convergence, okay? And of course, we can take nth roots of non-negative real numbers. We can do that. That's what you learned in college algebra and algebra 2, if you thought about it, or probably before then. Maybe you learned it in general math, even though you didn't like it at the time. That's when the thought of a complex number or actually an imaginary number started to percolate in your head. Now, just the same kind of proof, again, this utilizes the geometric series just like in the ratio test. This is also saying that as you get far enough out into the sequence, you get a non-decreasing sequence, which can't have limit 0. So the proof is the same here. If the limit as n tends to infinity of the absolute value of the generating sequence to the 1 over n power, the nth root, like here, is greater than 1, then divergence by the divergence test. And then lastly, the same song and dance, you can compare the same kind of series that we did before. If the limit is 1, then there is no conclusion. So then you would have to try something else. So that's the unfortunate part about the ratio test and root test. When you really need it to work, it doesn't always work. And you're like, man, that means I've got to get really creative here. And that's really what happens in math. Just think about the first time you did optimization problems in Calculus 1 and you were inscribing a right circular cone in a sphere of radius r. That's a classical problem like the fundamental theorem of calculus. I mean, those problems are difficult. I made up a problem one time in the spring, and I thought, kids, I should have just taken an easy problem out of the book. And when we solved it, I said, oh, okay, since we've burdened through this, I'm going to put this on the test. And boom, it was on the test. But the thing is, as you model problems in engineering and physics, you can come up with some really complicated examples that seem relatively harmless. But then when you start trying to analyze them in terms of calculus, they get difficult really fast. Okay, so again, the root test, put this on a note card like the ratio test, just side by side. They're basically the same, except instead of doing the ratio, you're doing the nth root. So we have the what? We have the name root test. So now let's do a couple of examples. I've got one powerful example here that I think will work well. So here's an example. Now again, the ratio test will stick with you. The root test will be kind of back in the rafters somewhere, but you'll still be good. So here we have the series n divided by natural log of n. Now, the reason I like this one is because it had some really interesting limits in it, and it gives me an opportunity to go back to L'Hopital's theorem. Now, when you look at this and you think about, okay, we've got ln of n, we have a power of n. Okay, the root test would get rid of that. And then you're thinking that leaves us with something like, n to the 1 over n. Well, that's a special limit. That's a special limit that was on that sheet, and I want to say a little bit about it that I provided for you back in section 9.1. And so when you think about this, that might be a good way to go, because otherwise with the ratio test, we may or may not have a particular ratio that leads to a simple analysis. So we'd have the n plus 1 and we have a power here, then we'd reciprocate. We may not have a limit that would be as easy to do. So you can try that, but I want to use the root test so you have a decent example of this. So in this case, test for convergence. And one thing about the WebAssign, they will often say, well, use this test. Okay, well, okay, fine, use it, unless you don't have to answer questions about it, use whatever you like. So test for convergence. And in this case, I'm going to say use root test. And I'll just say here, this power of n is kind of, why we're saying because of that particular term in the generating sequence. So now we have the limit as n approaches infinity of a sub n to the nth root. So this will be the limit as n approaches infinity of the absolute value of n divided by the natural log of n to the nth power. Now, of course, n starts at 2, so the natural log is positive, and of course, n is positive. So we can retire, if you like, we can retire the absolute values. This is clearly non-negative. So this will give us the limit as n approaches infinity. You use an interpretation that moves you forward, ladies and gentlemen. So here we got this. Again, positive terms, remove absolute value. Now apply laws of exponents. So we get n to the 1 over n. And now we have the natural log of n raised to the n power raised to the 1 over n. So now this equals the limit as n approaches infinity of n to the 1 over n. And of course, the n and 1 over n absorb, and we get ln of n. Now, this is what's interesting here. You're thinking that's a special limit here. This n to the 1 over n, that's a special limit. That's just nth rooting n. And we're thinking, when you start looking at this and you think about how we do this, you're like, okay, well, And what's interesting in this particular case is that what I've written here in this analysis that I've done is to think, okay, I'm at this point of the problem. If that fixes, and I know the log n is an increasing function, I would think that I might get a limit 0, but I don't know this. And so again, you're thinking, if this limit is fixed and this diverges to infinity, then I get 0. So we need to do an investigation. And I didn't do this before, so this opens the door to that. So we need to investigate this limit. And at the time, I didn't talk about it, so I want to go ahead and look at it. So here's what we're going to do. Investigate this limit. We think this is a special limit. So what we're going to do is look at the real analysis. Let f of x equal e, we don't do the e's yet, x to the 1 over x. And so we're thinking if we can write this problem in a way so that we show that the function actually has a maximum and then use the squeeze theorem, I think we'll be in good shape. So this is how we're going to do this. We're going to apply some calculus, but this is crazy. So here's what we do. We do the standard trick, e to the ln x to the 1 over x, which is e to the 1 over x times ln of x. Now, if you want to think about this, you're thinking this is a far better alternative. So now what we're going to try to do is get an upper bound for this function and then use the squeeze theorem. So you're thinking we could have used L'Hopital's rule, but I want to just give you a different argument here because you need to see it. So when we look at this, we're thinking, okay, we're going to let x be positive because that's what's going to make sense for this function. And so now let's look at the derivative. So now we get the function itself, e to the 1 over x ln x, and then we multiply by the derivative of the power. Okay, the derivative of 1 over x is negative 1 over x squared. That's just x to the minus 1 ln x. And now we take the derivative here, so this will just be 1 over x times 1 over x. So this gives us e to the 1 over x ln x negative 1 over x squared times ln x. I just thought this might be good. I came up with this when I was preparing for class, and I thought, let's let the kids see something different. So now this factors. So if you like, we can do the negative, leave the negative or take whatever, your choice. So let's just take the 1 over x squared out. So we're going to get e to the 1 over x ln x divided by x squared. And this will give us 1 minus ln x. And we've seen this before. That's where I thought about this. Now, of course, this is non-zero. E to the 1 over x is non-zero, and x squared is clearly non-zero. So this can be 0 if and only if, in this case, ln x equals 1. Well, what's a logarithm? Power of the base. The power of e that equals x is 1, if and only if x equals e. Now, the beauty of this is that you're thinking, okay, well, this is kind of like a problem we did before. There was one like this in section 1, but I didn't cover it explicitly. You did it in your homework. So now when we go back over here, we see what is this? What is this number? What does it define? Well, you just do a little sign test. So we've got 0 here, and we have e here out to infinity. Now, when you think of a number here, you can just think of using a 1, so to speak. Well, 1, of course, this is positive. And here, this would be positive. So you just did a test point of 1. We get plus, so we're increasing. And then, of course, something bigger than e, 2e, this is positive, but that will make this negative, just using the laws of logarithms. So our first derivative test implies relative maximum of f of e, increase, decrease, which now is just what, where's my function? E to the 1 over e. Isn't that weird? E to the 1 over e. That's a real number. And so now what we're seeing is that this function is actually bounded, therefore this function is bounded. So then, and this is where we can use something that's very simple. We're going to investigate this. So note, we have 0 less than 1 over ln n, or n to the 1 over n. But this has an upper bound of e to the 1 over e. But now, of course, when you look at this, both of these limits will be zero. That is, the limit of zero is zero. And then, of course, the limit as n approaches infinity of e to the 1 over e divided by ln. Well, the e to the 1 over e is just a constant, so we can factor that. Of course, now ln tends to infinity as n tends to infinity, so this is 1 over infinity. So this is e to the 1 over e times 0, which is 0. So by squeeze, the limit as n tends to infinity of n to the 1 over n over ln n is 0. So, I mean, clearly, this requires more than just like, oh, okay, the limit's 0, because I think it is. I mean, once I've done it, you know it and you can use it. It's probably not going to be the case that I'll see this type of analysis on the test, because you all haven't had me for previous classes, and this is not something you do readily. But the thing is that now you have this extra tool to say, okay, even though I know this is a special limit, now I know what the limit is and I'm good to go. And so I look at this and say, okay, well, this limit is 0. Because when we think about this particular example here, and we consider what's going on here, this is a bounded function as n approaches infinity. And if you go back and look at the special limits in the notes, this limit is 1. So the beauty is that you don't see this unless you do some type of an analysis. But now, as we back up here, we say this is clearly less than 1. So we say series converges absolutely by root test. So now, again, this requires a little bit more work than maybe we thought it would. So we use the squeeze theorem to get this limit down here. So here was our analysis. So you might be thinking, well, I don't like the root test if we have to do this. Well, it's not always going to be as complicated, but I want you to see that when we consider this, we can think of just applying the limit upstairs and the limit downstairs, knowing that this is fixed and that this diverges to infinity, or we can just go ahead and process the entire limit, not even thinking about breaking it up like I've done here with the squeeze theorem. I just needed to show that this particular function here was bounded. And once I have that, I can do the squeeze theorem. Without the bound, I can't use the squeeze theorem. So that's the beauty of this result. And that's why I wanted you to see a really nice example of the root test. Of course, it's that everything has a power of n in it. They're all gone and you're left with a skeleton of what you started with, and it can be even simpler than this, or much simpler. So these types of limits you will see in physics, you'll see in engineering, and I want you to be aware of them. There was a really neat book that was utilized at the University of North Carolina after my undergraduate days that is still presently in use, and it had a little section where it said special limits, just thrown into the chapter on series special limits. And I thought that's a great little section because it just showcases some limits that come up often that I've even shared with you that we're going to use again. And these special limits are the difference between moving our logic forward and just, being stymied, so to speak. Okay, so that's the root test. So enjoy the root test and the ratio test. I think that'll be a nice diversion. I should say a nice divergence. Sorry, the humor is terrible. A nice diversion from what you've been doing. Now, the next topic is probably a personal favorite because it's starting to get into the subject of why your calculator works. And I want to share this with you. Now, again, like I did before, I just want to give you the statement of the actual theorem and give you a nice copy of it. Here we go. Yeah, I'll do this and then we'll talk about the actual justification for this. Like we did before, we'll do an example and then we'll cover the justification. So I don't want to kind of scare you with the proof yet. Now, the idea here is that you know that there has to be some monumental result, ladies and gentlemen, that had to come down in the calculus. I mean, every time when I teach pre-cal, I'm like, okay, let's go to the Google calculator to get our calculus approximation. And they probably think, why does he keep saying calculus? Well, your calculator works because of Taylor's theorem and infinite series. Ladies and gentlemen, you don't have magical computer robots that sit in your calculator that calculate things. Everything that's computed on a calculator is arithmetic, okay? And so when you do natural log of 2, or you do the sine of, I don't know, 3/4 radians, you get a decimal approximation of that. That is an infinite series. That is a Taylor polynomial that's extended to enough terms to give you 9 decimal places. Or if you got the Google calculator, you even get more than that for free. So how does the calculus help us do this? And you're thinking, this must be fairly tedious. And it is, but it's doable. So this is what we call the Taylor polynomials. And we're going to talk about specifically Maclaurin polynomials more, but I just want to give you the statement of this theorem. And I want you to write this down as I go through it. This is very important. This is called Taylor's theorem. Now, Taylor was a mathematician post Leibniz. And so what many mathematicians did after the invention or discovery of calculus is they just moved the subject forward. They said, okay, well, now that we have the calculus, let's just see what we can do with it. And so here's the deal here. What we do is we start out with a natural number n, and we have some interval I, a to b. Okay. Now I've written some stuff in pencil here, and I'll show you, tell you what that is. And I've got a little diagram here to make things make sense. So we're going to suppose that that f, the function f, has continuous derivatives through order n. What that means is that we call f Cn. Let me just give you a notation for this. We say f is basically contained in the Cn functions. That is, we have that many derivatives are continuous on the interval AB. So if something was C1 on the interval, say 0 to 1, that would mean when you took the first derivative, it was nice and continuous on the interval 0 to 1. So what this theorem says, and the thing is that some functions we deal with are C infinity. That is, you can take derivatives of any order and still have a continuous function. You know, e to the x, sine x, I mean, those are C infinity. So what we need, and this is what students think, it's like, okay, so functions have to be fairly well behaved, at least in order to do this. There's always questions on the WebAssign where you have a little video and the guy that maybe talks like Professor Ron, but has a whole lot more hair. You know, like me, he talks with his hands. He says, now listen to what I'm saying. And it's like you just like, okay, I believe you, I believe you. But then they ask the question and you miss it because you didn't listen. You just watched, but you didn't listen. So here's one of these things. We must have a function that has continuous derivatives through order n. So maybe we need 3, 4, maybe we need C infinity on this interval. And then we're not going to be too picky. The n plus first derivative just needs to exist. Okay, so we basically need a very well-behaved function. It doesn't have discontinuities, it has derivatives, and the derivatives have no discontinuities. So this is what we mean here. And we deal with functions like this all the time. It's just that we really haven't characterized. When we did the arc length, ladies and gentlemen, remember, we needed C1, we needed f prime to be continuous so that we could integrate the square root of 1 plus f prime squared. So we've already dealt with the C1 function with the arc length. And then of course the surface area, which was based upon that. So then, and of course we only need the n plus first derivative on the open interval, but so much, you kick out a couple of points. Then, and this is where it gets a little complicated, but the formula is easy to remember. For any x in I, I've got a little diagram here, and this is A, and this is B. I add stuff to, the notes that I post, and then I go back and repost them and add the additions or whatever. Add additions, that's real redundant, right? And so then what you have here is for any x in this interval, there will exist, again, notice up here, let me see here, with my statement, I just want to make sure that I have, here, notice what I've written here, an interval I containing C. I've got that double underlined. I just wanted to make sure I had it printed. See that? Containing C. I didn't mention that because I was talking about this. So C is on this interval. And so for any x, I just colored in an x, there is a z. That's from the theorem. There is a z between C and X. Now, I don't know if X is less than C or bigger than C. I don't know that. So we just say between. We don't know. So there's a Z between C and X. So again, C is in the interval. We take an X in the interval, usually not equal to C, just because we want to go somewhere with this. And so Taylor's theorem says, if that's the case, there is a Z between C and X such that, and this is the polynomial here, this is the arithmetic of the calculator. F of X equals F of C plus F prime of C times X minus C. So you can think of C as a center or expansion point. So you're thinking, okay, well, I've just got F of C here, that's a constant. I've got F prime of C times X minus C. So I take a derivative of f and evaluate it at c and multiply by x minus c. The next term is f double prime of c divided by 2 factorial times x minus c squared. Oh, okay. So if I keep going, the nth term, so to speak, well, the n plus first term, because that's number 1, that's the 0 term, and then 1 and 2. So when I get up to this term, I've got the, okay, Cn, I've got the nth derivative evaluated at C divided by n factorial. It's like I'm taking derivatives of x to the n and getting an n minus 1, n minus 2, and getting n factorial, divided by n factorial times x minus c to the n. So basically what we're getting is a function that agrees at f at all of these points. That's amazing. I mean, someone just thought of this and then said, is this actually something that has some legitimate mathematical support? Okay, so you have all of this. So what's going to take up the extra, so to speak? What's going to fill in the parts that don't get taken care of by these terms? It's this term right here called the remainder, the R sub n term. Now, What I've written up here is that this part right here is what we call the nth Taylor polynomial, right here, of degree n, right there. So it's got n plus 1 terms. Well, some of them might be 0, but here we have n plus 1 terms. And then you're thinking, this is what kind of fills in the gap that doesn't get covered here. This is called the remainder term. What does it look like? Well, that's where the z comes in. The z between c and x, we take the n plus first derivative of f, evaluated at z, divide by n plus 1 factorial, and multiply by x minus c to the n plus 1. Now, basically, with this theorem, you are replacing the function f with a polynomial. You're thinking, how is that? Well, the idea is that this polynomial is set up in a way so that it agrees with the function at n plus 1 points. And so you're thinking, the more terms here, it's a polynomial, and we're not too far away from c, the more this function is going to closely approximate f. We're thinking, well, if we just have a linear function, that might not be the best, but then we go to a quadratic, power 2, then we go to a cubic, and then, even higher. We're thinking, if the function has the Cn, because it's not going to work for any function, but the Cn, then we're thinking we can improve the replacement, so to speak. We can improve the error by developing more terms. And then you're thinking, okay, this remainder theorem here, this remainder term will be what we have to analyze, in the sense is like, how big can this be? We're thinking, oh man, Professor Ron gotta figure out what this derivative is, and kind of figure out basically how big this can be, just like we've done before with the alternating series test, the first neglected term, and then the improper integral for the integral test, where we go from n to infinity to figure out how big the error can be. How many terms do we need to make the error less than maybe 1 over 100 or 1 over 1,000? And this can be characterized by this remainder theorem here. So here's what I want to do. That's the theorem. And before we actually talk about why, I want to do some examples. So when we think of Taylor's theorem, let's just do it. Let's write it down. Let's just practice writing it down. You will need to know this. You will need to know this. So start writing it down every day. Students will go back to Taylor's theorem where they forget everything else on the final exam and say, well, I can compute the Taylor coefficients and I can get this problem right, and exactly right. Because every convergent power series is its Taylor series. We're going to extend these polynomials to an infinite series if they're C infinity. And then we're going to figure out that a convergent power series is actually the Taylor series. So they are not any different. So when you have a convergent power series, it's the Taylor series. So however you come about developing coefficients, they'll all be the same. So that's when students say, well, I've got Taylor's theorem. I'm not left in the lurch. I can always use that. So remember, this will be f of c plus the first derivative evaluated at c times x minus c. And then you write this down a couple of times and you'll be professionals. The second derivative, so you're thinking you have to compute some derivatives, and hopefully the derivatives are easy. In some cases, they're very easy, divided by 2 factorial, x minus c squared. I'll write down the cubic term. I didn't have it in the statement of the theorem. Now, what usually mathematicians do, once you get to like 3 tick marks, what mathematicians will do is just put like a 3 up there for the third derivative. Your choice, but I think it makes it a little bit easier. Evaluated at c, 3 factorial, and we keep going to the nth derivative. That is, we need Cn functions, nth derivative at c divided by n factorial. Oh, sorry, left out my factor here. Here, let me put that in. I can't squeeze that in. X minus C to the third, very important, plus, and then the nth derivative, I'll put the remainder down here. I'm going to run out of room. And then plus the remainder, where Rn of x equals the n plus first derivative evaluated at z. Remember where the z is between c and x for every x in the interval. Where z is between x and c. That's the best we can do, ladies and gentlemen. We don't know which is bigger, so that's, you're thinking, well, why do you say it that way? Well, because that's the best we can do. So z is between x and c. So again, this is how your calculator works, and there are variations on this. For logarithms, there are often adjustments in infinite series to make them converge faster, because we know the logarithm kind of takes its time. But these form the core of how your calculator works. So we basically replace the function with a polynomial, a transcendental function with the polynomial. And then you're thinking, well, we can do rational functions. We could use the geometric series and to adjust that to get nice power series. So this is kind of the beginning of the power series revolution, so to speak. So again, when it comes to working with these kinds of problems, before we talk about why it works, and I'll say more about that, I want you to be comfortable with how it works. So this, again, just think as you write it down. This function has to be really in good shape. I've got to be able to take n plus 1 orders of derivatives. So I hope I've got C infinity. And so it's easy to remember if you just remember the factorial corresponds with the order of the derivative. So first derivative, 1 factorial, we don't write it. Second derivative, 2 factorial. Third derivative, 3 factorial. Nth derivative, n factorial. N plus first derivative, n plus 1 factorial. And remember, this is where that interesting z number that falls between x and c enters into the formula in the remainder term. So we say f of x is the Taylor polynomial here plus the remainder term. So this part here is the Pn of x. And this is what we call the nth degree Taylor polynomial. Now, when we take the expansion or center C to be 0, when, and you don't have to do this, but you will see this terminology, when C is 0 and we expand about 0, the center is C, we say, this is Maclaurin. We say Maclaurin. Maclaurin is a Scottish name. Maclaurin polynomial. So that's just a special name given to the cases where the C is 0. We spend a lot of time with polynomials and series developed around C equals 0. That's a very, very useful center or expansion point. So that's, this dude actually studied those more. And so his name carries the C equals 0. But they're still all Taylor polynomials. We just distinguish when C is 0, okay? So let's look at some examples. I cannot emphasize how you need to know this and understand it. because it is the linchpin of analysis. When it comes to differential equations, solving higher order linear differential equations with variable coefficients, the infinite series allow you to make solutions. And this theory is critical. It is critical. So this is the beginning of it, and the beginning of how that fancy calculator that you spent probably too much money on works. Or maybe you didn't, I don't know. Some of you I know have some fancy calculators, but that's why they work. So I just say use the cheap Google calculator and do everything by hand, and then you're going to be better off. But it is what it is. So let's look at some examples here. So here's our Taylor's theorem, just the conclusion, so to speak. So let's look at some examples. The theorem proof itself is very doable, but you don't want it right now. You want to be able to see some examples, and then we'll go back to it. So I'm going to pick some of these WebAssign problems here. I mean, basically, when you take the derivative, we have to apply Rawls' theorem, just like we're doing the mean value theorem or extended mean value theorem, to a function. And then when you take its derivative, of course, it telescopes. And that's where you can basically generate the formula for the remainder. When we think about this, ladies and gentlemen, the issue is not this part. This part is just rigging a formula that agrees at n plus 1 points, so to speak, or at n points. Excuse me, n plus 1 points. This is the key right here. This guy right here is the focal point of the theorem. This is why it works, because this is why we can say equals. And trying to find the z may not be something we can latch on to exactly. We know it exists, so we have to get upper estimates of this in an absolute value to be able to generate errors. So this is the key to the theorem right here, the remainder. Now let's look at a simple example. Let's just compute a Taylor polynomial to get used to this. So here's an example where we have f of x equal cotangent. And then, of course, when you have all those powers, do you always have to reduce them? No. If the powers are small, fine, reduce it. But if you got, x minus 2 to the 5th power, don't expand it. Just write it in that form. That's okay. That's not a problem. That's really preferable. So we always want to say, well, how far do we have to go? WebAssign will look at what you've done, test it, and if it's equivalent, you get your green check, which we all want. So we have a cotangent function, x. We're going to expand about pi over 4. Now, the cotangent is cosine over sine. And so we have to stay away from zeros like x equals 0, x equal pi. So if we did an expansion here about pi over 4, that's good, but we got to stay pretty close to pi over 4. We can't venture out too far because then the function becomes infinite. So in this case, we're thinking about staying relatively close to our center point or expansion point, considering what we did in pre-cal and cal 1. So here's what I want you to do. Let's see, this is simple. Let's just get practice with this. Let's compute, in this case, the first degree Taylor polynomial. So this is P1 of x. So this is the first degree Taylor polynomial. So when you look at this, the best thing to do is to look at the actual formula for this. Now we don't have to evaluate the remainder. We're going to do that in some other problems. So now we see that P1, let's just write down what it is. And this doesn't require a lot of derivatives, so we don't have to make tables and things. So P1 will be f of c plus f prime of c times x minus c. That's the general formula for the Taylor polynomial of first degree. So for our problem, we'll have P1 of x equals, in this case, we're going to say cotangent of pi over 4 plus, now we're going to have cotangent x prime evaluated at pi over 4 times x minus pi over 4. Now, since this is low degree, we can just go ahead and write this out linearly. If we had second degree, third, or whatever, yeah, we might do a little table and fill everything in because that'd be a little bit arduous. Now, remember, we have like a 1 factorial here, but we just leave it out since it's not going to change anything. So now, again, cotangent here, cotangent of pi over 4 is 1. So we have 1 plus. And now the derivative of cotangent is the negative cosecant. So negative cosecant squared x evaluated at pi over 4 times x minus pi over 4. So this again is very rudimentary. We're just filling in the details. So now we've got 1 plus, so we've got minus here. So we've got, again, cosecant. So you can write this, if you will, as cosecant of pi over 4 quantity squared times x minus pi over 4. Now, what's interesting about this is that we haven't done anything past Cal 1. The only Cal 2 part is that we believe this. We believe it. So now, cosecant of pi over 4 is just square root of 2. So this is 1. I'm going to put all the steps in so you don't get bamboozled by this, so to speak. So now we've got the square, so that's just going to give us a 2. So we have 1 minus 2 times x minus, so you're thinking this is like a recipe, and pretty much is when you're just computing polynomials. So this is 1 minus 2x plus 2 times pi over 4. So we can write this as 1 plus pi over 2 minus 2x. Now, again, this is a first degree polynomial where we have a constant term and the x term. Now, again, when we think about using polynomials to approximate functions, maybe not the best, because for instance, if we want to be able to venture out, say, let's think about this. We can't hit 0, so we could think about here, pi over 4 and have a nice symmetric interval, say 0 here, and that'd be hard to do because that's the function's becoming infinite. And then maybe a pi over 2. But as long as we stayed, say, in a nice symmetric interval close to this would be fine, because here, this defines an asymptote, vertical asymptote of cotangent. So when we start thinking about these polynomials, we don't have the C1 here. That's a bad place, that we don't even have continuity there. So we're thinking of staying fairly close here if we're going to do approximations. And since we have a nice periodic function, your calculator has to work a little bit harder. And what it might do, just to save some time, is use the reciprocal nature between the tangent and the cotangent, you know, or whatever, just to maybe cut down on the amount of code. So when it comes to computing polynomials, this is a straightforward process. Now, one thing that I want to do kind of quickly here, just to finish up, let's just look at a nice simple one. So here's one that the derivatives aren't very friendly, just got to work them out. Not a lot of pattern here. Say we just wanted to do a Maclaurin polynomial of degree 3. So here's a quick example. So we're going to say our friend sine x, Cotangent's not as user-friendly. Sine x is very user-friendly. And we want our n equal to 3, and we're going to take c equal to 0. So this is basically the third degree polynomial, which we call the Maclaurin when c is 0, but just say third degree Taylor. Third degree Taylor, or Maclaurin. Now, if you see Maclaurin, they say Maclaurin, you just set c equal to 0. So now you're thinking, well, this is my friend, Professor Ron, let's write this down. Like, yay, I like this. So here we have n. We're not going to look at the remainders yet. That we're going to have to get a little bit better, do a little practice for next class. And then we have the degree or the derivative. And then we want to evaluate, then we'll utilize our formula. So we have no derivative, first, second, third, no derivative sine x, sine of 0 is 0. Remember, sine is an odd function. So we better have a polynomial that has what? Odd powers. You know, ladies and gentlemen, trigonometry is a beautiful subject, and we're going to see that all of this is consistent with what you've already done. The derivative here will be cosine x, cosine of 0. So this is where we tabulate things because we just have more stuff. That's 1. Then we have negative sine x. Negative sine of 0 is 0. And then another derivative, we get negative cosine x. And negative cosine x of 0 is negative 1. So this will give us what we need. So now P3 of x is f, and we'll go ahead and put it, now that we're professionals, we'll just go ahead and fill everything in, or at least thinking about it. Well, let's write it down in general. F of c, f prime of c, x minus c, plus, well, and of course here, let's just do this. Let me just save you some time. Let's just go ahead and take the c equal to 0 and save everybody some time instead of writing it down a million times. So we're going to have f of 0 plus f prime of 0 x plus f double prime of 0, 2 factorial, x squared, plus f triple prime, or the 3 of 0, 3 factorial, x cubed. So again, c is 0. So x minus c becomes x, evaluation at 0. So now let's fill everything in. So the first term is 0 because this is just f of 0 here. So we have 0 plus, so now we have a 1 times an x. F double prime here is 0. So this is just plus 0 times x squared. I'll put the 2 factorial in so you don't forget it. And then for the third derivative, we have negative 1. So we have minus 1 divided by 3 factorial x cubed. So we have if and only if P3 of x will be x minus x cubed divided by 6. Now, what we see here, and this is the development of the polynomial for sine, and then you're thinking, okay, this is an odd function, as it should be. Sine, by definition, well, you can prove it with the unit circle is odd. We should get the same thing here. So what we're going to see is we extend this to the infinite Maclaurin series. We just get a bunch of odd powers of sine, and sine of 0 is 0. The idea here, ladies and gentlemen, is that now we are going to develop polynomials that replace the transcendental function. They replace the transcendental function. And therefore, the computation of values becomes arithmetic. And that's how all of these fancy calculators and computers work. And when you tabulate things, this is what's going on. This is what the computer is using. So now if you want to think about this, do the same thing for cosine. You just get a bunch of even powers of x. Do a Maclaurin polynomial, third degree for cosine. Now notice what you're seeing is that all the even powers, so to speak, the zero power, the even, they're zero coefficients. They go away. So when you do the cosine function, all the odd powers have zero coefficients. So this is good. When we look at this, we think, yes, we feel good about this because now this is supporting what we think or what we already know from Calculus 1 and pre-calc. So what we'll do next class, I'll go over some of the ideas of how the proof works. I think I'll look at the derivative and show you that it telescopes. And then what we want to do is analyze the remainder, do some other polynomial calculations, and then analyze the remainder and see how we can say, okay, if we have this many terms, what kind of error are we going to get? Or if the derivative is simple enough, can we figure out how many terms we need for a certain error? So what you're going to see when it comes to the polynomial here is this is the issue. When we try to approximate this, this is difficult. This term is the part that makes the process of utilizing Taylor's theorem difficult. And when we can't get a handle on the n plus first derivative, we have to use other means. We see that with the binomial series, which we're going to talk about at the end of this chapter. So again, I hope that you're excited about Taylor polynomials. We'll segue this into power series and representing functions by power series. And then we're going to make a nice general list of all these power series, which will basically be Taylor series. So remember, in our parting, every convergent power series is its Taylor series. That's actually easy to prove. We just wish that the proof of Taylor's theorem was simple. So I appreciate your attendance today. So go ahead and complete your homework and your quiz, or get that out of the way so you can start spending some time on this. This is essential material. This is one of the hallmarks of the Calculus 2 course that brings you into the realm of doing mathematics on a more sophisticated level. So I appreciate your attendance today. I hope you enjoy this material as much as I do. I love real analysis and topology. When I was working on my master's thesis, I had a department individual in topology say, Professor Ron, you need to stick around and do a dissertation in this area. And I said, well, maybe when I'm 100 years old, I'll go back to school. But the idea here is I hope you enjoy this. This is going to be fun material. Everybody have a good day.